that. Right. Okay, so I'm going to give it just a little bit longer for some people who are just joining, and I'm getting lots and lots of answers. So we have organic synthesis routes. Absolutely. Isomerism, interesting one. And then remembering all the conditions. So I think that is one of the real big challenges with organic chemistry is the quantity. Sneaky things in the questions that you need to be careful about. Okay, I mean, examiners are sneaky, right? Very, very sneaky. Mechanisms, absolutely. Different reagents, problems, yeah, working stuff out. Okay, so the 6-mark questions and synthesis routes, definitely, they are pretty challenging. And so what we're going to look at today is the first little part is actually about how we work on our revision, how we actually get that revision to support the best way to actually approach those exam questions, which is not always going to be diving straight into the exam questions. So we're going to talk about that today. Maybe we dive into the exam questions before we're ready. And some of the other problems we're talking about, like remembering everything, if we don't remember stuff, we're never going to be able to do the synthesis questions, right? So we don't remember the individual parts, we'll never be able to put them together in a sensible way. So that's why organic is so big, right? It's huge. There's a lot to it. It feels like a lot. So we're going to try and see if we can get some good techniques. The second half, we will look at exam techniques specifically. So we will be looking at how we approach sneaky things in exam questions. Someone said, like what words to look out for, and some common mistakes that people make in those as well. Okay, I've still got more people popping in, but I'll keep an eye on my waiting room and keep adding people in. So just to say that the first half is just about the revision sites. Okay, you can ask questions whenever you like. I will try and keep an eye on that, as well as the list of admitting people. So we're going to look at like some common difficulties and mistakes with revision specifically. So it's not about exam technique, this first part. We're going to look at retrieval practice. I'm really big on that. So if you're on my mailing list, you'll know you get one of those every week. We will look at specific ideas for how to keep testing your brain for organic to try and get that stuff to stick in your head. And then how we like actually plan our revision. Now is a really good time to be planning ahead because we've got a certain amount of time. It's quite a long amount of time still that we have. That's another thing we need to remember. And then we will move on and look at exam technique specifically in relation, well, to paper 2 and paper 3, but definitely to the bigger organic questions. Okay, so let's look at where we go wrong when we revise organic chemistry. And I'm not saying that you're all going wrong, because just because we get stuff wrong doesn't mean we're revising wrong. But organic chemistry, like, we could be making some common mistakes. So too little, too late. We know that one, right? Are we guilty of that? I mean, it's not ready. We're not ready for the exams yet. They are still nearly 2 months away. Hang on, wait, no, more than 2 months away. Okay. So I guess the only thing I would say about too little, too late is perhaps we know if we're in year 13 that we maybe should have spent more time going back over the year 12 stuff, which is why I always send out the retrieval quizzes, and they always have quite a bit of organic chemistry in them to make sure that people are actually doing that stuff. Okay, so if we are guilty of a little bit too little, too late, if we can remember nothing at all about alkanes, alkenes, haloalkanes, and alcohols, never mind. That's okay. We still have time because we've got a couple of months to go. But maybe you don't realize there's also such a thing as too much too soon when it comes to revision. And what that means is you're going, right, I've looked at my notes, I've kind of got an idea I remember what an alkene is. Right, time to crack on with some past papers. So give me a thumbs up if you are a big past paper person. If you spend, like, basically to you, revision is past papers, either physics and maths tutor or study mind, save my exams, not quite past papers, but are you just literally all about like adding extra things on? Are you like always doing that? So, and I've just had a question, which I'm going to address because, which is basically, is this a repetition of my video from 11 months ago? Well, funnily enough, like people want, people are doing their exams at different years. So that's why I said this is specifically for students who are taking like their exams this year, or who maybe joined as a year 12 last year. So yeah, I absolutely did say that it's going to be very, very similar, with the opportunity for you to ask questions. So that's what you get added if you attend a live chat. But if you've already watched it and you feel like there's nothing more, then feel free to drop out. Okay, going back to what I was saying, too much too soon. Yeah, past papers, we don't want to rush into those. And then another thing that we do, so we probably don't feel ready to do a paper 2, but maybe instead what we do is, I've just done my revision on alcohols, so I'm going to do all the topic questions on alcohols and focus on an individual topic. But what we've probably noticed with things like synthesis, with mechanisms, and with big spectroscopy questions and analysis, is they're not going to ask you just about alcohols, really. They're going to ask about lots of different things together. And then the other mistake that we do is we make our revision a little bit too easy. So if we're finding that we are doing lots and lots of work, you're like doing lots and lots of revision, you're putting in some hours there, and it's not sticking, then part of that is perhaps because what we're doing isn't hard enough for our brain, and we're not actually really making our brain work hard to retrieve the information. So examples of things that you might be doing that are mental shortcuts is, you've got a pile of flashcards, you look at the front of the flashcard, or you're on Quizlet and you look at the term and you're going to define it, and instead of writing it down, or saying it, you just kind of mentally in your head go, yeah, I know what that is. I know what a structural isomer is. And then when you turn it over, you are confirmed that you got it right, even though you didn't write it down, so you couldn't check it properly. So actually get and write stuff down when you're revising. Do not try to keep it all in your head, because it doesn't actually, your memory, if your memory wasn't accurate, then when you look at it and you check your answer, you're going to just assume that you got it right. The other thing, yeah, that you're probably not doing is just not enough of retrieval practice. So I will give you some ideas of how we can apply that. But first of all, what do I mean by retrieval practice? How is that different to doing past paper practice questions? So, what am I actually practicing when I say retrieval practice? What's the point of it? Loads of research about it, really, really popular in sort of education circles, but some of your teachers might use it a lot, but you need to be doing it as well. So what's the difference? How is it just not quite the same as going, right, I'm going to do all of the questions on organic chemistry, or I'm going to do a paper 2 practice paper? How is it different? Any ideas? And if you're not sure, or you need to go and do some more of my quizzes. Okay. So, and certainly those of you saying, like, how do I memorize? This is how we memorize. So we are trying to just bring back information. We are not necessarily trying to apply it to a really difficult context that we've not seen before. We are not trying to work out how to do a weird mechanism or how to plot a synthesis route. All we're trying to do is literally get in all the stuff that needs to be in there in order to do the past paper questions. So to get stuff into your head, you have to get it out of your head and you have to practice getting it out. And that's all retrieval is. It is strengthening your nerve endings, your synapses, and everything, and your connections in your brain so that you're not testing application, because that's a separate skill, which you still need to do. But retrieval practice is just simply, okay, what are all the reactions that haloalkanes do? What are the reaction conditions for these 5 different questions? So short, simple, quick recall. You can do it anywhere, anytime. And you've got to get your brain in a good situation. So if you sit down now and try and do a paper 2, it's going to be really hard unless you've really well prepared already. And if it's really hard, you'll get stressed. And to be honest, you won't do your best. You won't remember everything. And you will then have kind of wasted your paper 2. So it's best if it's random. This is why in my email list, I send out a weekly quiz, which is random questions every single time. So you never know what the topic's going to be about. Because if you know that you're sitting down to do questions on like benzene, then your brain already knows and is ready for all the questions about benzene. And therefore, that doesn't happen in an exam. You're doing questions about benzene and then something pops up that's different. Okay. I'll talk about the weekly emails and stuff at the end if you're not already on that. Retrieval practice should be little and often. Obviously, it's going to be a bit more right now because we're getting ready for exams, or a lot of us are. And it should be low stakes. So what I mean by that is we're not giving ourselves marks. We're not grading ourselves. We're not giving ourselves an A, B, C, or D grade. We are simply just trying to remember it. It doesn't matter if it goes wrong. So that seems weird. Like we kind of always think that if we're getting lots of stuff wrong, that somehow our revision is not effective. But if we're getting stuff wrong in retrieval practice, it still works. You're still practicing. So I just want to point out low stakes doesn't mean easy. Okay, so low stakes means you're not putting pressure on yourself to perform. You're not grading yourself, that kind of thing. Low stakes is also not time pressured, because that is an exam practice skill. But it doesn't mean it's easy. So you still got to work quite hard, which is why I'm suggesting writing and drawing stuff out when you do it. And getting it wrong is like part of it. So basically, this idea is that you could be sitting down and writing everything you know about a particular functional group, like alkenes, everything you think you can remember that's important. And if some of that is wrong or missing, that just strengthens those synapses even more to go, oh, I got that wrong last time, so I'm going to remember it next time. If you keep getting it right, it's not very effective. So move on to something harder. Okay, how do we do it with organic? Let's have a look at, oh, scary, reaction pathways. Don't worry if you don't recognize every single thing on this. It's just a generic organic reaction pathway, so it's not specific to any one exam board, right? So some of these things might not be. Most of them are things that you should know. So if you've got this is easy to find online, this kind of reaction pathway. What can we do with it? That would be great retrieval practice. So one is you could draw the functional groups. So you could write underneath. You could make sure, just that you can simply draw aldehydes, ketones, nitriles. Make sure that you can do a displayed formula, maybe skeletal, try different ways. Then, of course, all of these arrows have reagents. And all of these areas have conditions. And when we look at exam practice, we're going to talk about what the difference is and what sorts of things we should be putting there. You could put type of reaction. We'll talk about type of reaction later as well. Some of these you may have to write the mechanism out, so we need to be able to do that. And then once we've got confident with filling in any of those pieces of information anywhere, we can then go back to go, okay, what about, so this is how we build up the synthesis skills. Can I now do multiple steps? Okay, so can I now go from alkane to nitrile? Or can I go from alcohol to amine? How do I know the individual steps? So you can start to build it up rather than giving yourself like a full big set of practice questions. There is the one benefit of having so much to remember for organic chemistry is how easy it is to test yourself, whereas other things it's not so easy to make up questions for. But this one it is. So if you've downloaded the little free workbook that I sent out, it's not got a great deal in it, but it gives you the idea. So all of the questions, they are set up so that you have one side of the page, which is like the question, like structural formula of whatever, or skeletal formula of a particular name of a molecule. And then on the other side is the answer. And you can fold that over, you can print it out, fold it over, and you can basically test yourself by going down, practicing it, actually drawing it out, and then checking on the other side. That is super easy to do. And therefore, you could do that with any of these parts of this diagram. I've also got loads of resources on the website where you can cover stuff up with Post-it notes, test yourself on the different things about each type of reaction, lift up the Post-it note and check if you got it right. So all these things, they seem really simple, but they are incredibly effective if you keep at it, bearing in mind that you've got a long time to keep at it. You can then take an individual functional group. How many questions can you ask about one functional group? I just picked alcohols, but it could be any. How do you name it? How do you classify it? Is it primary, secondary, tertiary? Really good question. Do posters help for these? So depends how you do it. Okay, so having those big organic maps, writing them out is okay. But if you're just doing it from your notes and all you do is make the poster, then what? Like, I've made loads of posters in my time. I don't remember what's on them just because I made a poster. So you've got to use it afterwards. Post-it notes great for that. If you make that poster and you stick Post-it notes all over it, and then you try and remember what's under that middle Post-it note and look at the actual specific information and you write that down, that is effective. But just making a poster on its own, it's going to be better than doing nothing, but minimal effectiveness if you don't use it. So all of these are what I call retrieval prompts. These are questions that you can ask yourself about any functional group, which will also really help for those longer questions where the information gets more synoptic. So how many of you, when you're revising functional groups, actually think to yourself, oh, I wonder what the boiling point is of an alcohol compared to a carboxylic acid or an aldehyde or an alkane or an alkene? You get asked those questions and you know how to answer them based on things like hydrogen bonding, intermolecular forces. You should be revising that at the same time that you revise your organic. It's part of the same chemistry. It's part of how we separate things by distillation. So therefore, you're going to get asked about it. The type of reactions, we will look at those in a moment. Reagents and conditions and equations. That's something that's really missed out. Like you have to write not just mechanisms, but balanced equations for organic reactions. And I feel like we don't do those as much. We're not as good as doing that as we are for, say, transition metals, where we know we've got to write out all the different reactions and equations. Mechanisms, of course. So unfamiliar mechanisms, we're going to talk about at the end when we look at exam technique. But the familiar mechanisms, you've got to get those down before you can worry about the ones that come at the end of the exam paper that you haven't seen. Same with isomers. There are some mechanisms where you just know you can get different products, like the 2H and the Br can be the other way round when you add to an alkene. So those are questions you can ask yourself when you're doing the revision. Do these reactions have any possible other products? You can also ask, how do you make this functional group? Loads of people always think about starting somewhere and ending somewhere else. But when we do synthesis, the best thing is to work backwards from the thing that you've made. So just changing that question to how do I make an alcohol? How do I make an amine? How do I make a carboxylic acid? Is a really good trigger to your memory so that when you get to the exam questions, you will be much better. And what are the chemical tests? So all of this is just one functional group. These are all the different questions you can ask about it. And then be so much more prepared. And then when it comes to an IR, an NMR, mass spec. Now, obviously, that is a separate skill. You can't say alcohols always look like this because, of course, it depends on their whole structure. But what you could do is go, well, I do know what it looks like on infrared. It's got a particular bond. Maybe I do know a little bit about what it looks like on an NMR because the OH has a peak on NMR. And maybe I can think about the OH peak on a mass spec showing up like a fragment of 17. So all these little questions will help you just to, for a start, they're going to mix up your revision. If you just keep doing practice questions, it's good. Practice questions are great, but they're quite boring. And this is a way to mix up your revision and still be doing effective revision, still properly testing yourself. If I'm asking myself any of these questions, I need to be writing it down. A whiteboard, it can be on a screen if you prefer using like an iPad or something like that. Just a bit of scrap paper. It doesn't matter. Excuse me. It does matter that you're writing it down though. You're gonna have to write it down when you get to the exam. You're not gonna wear your arm out, or you might wear a few pens out, but that's okay. I'm sure you've got loads. Okay. Before we move on to the exam technique, then just a last bit about that planning stage. Again, if you're on my weekly email, you know I've sent out like a revision planner. The revision planner started in March, but it doesn't matter. You can catch up. So just spread out the March topics into April, and you've still got loads of time to cover them. But in that, it also talks about this mix of types of revision. So from today, this is paper 2, just because this is specifically about organic. If you want to make it about paper 1, just take off 8 days, because I think it's 8 days before. So we've got 76 days till paper 2. That's a lot of days. Some of them you'll be in school, some of them you won't, some of them you'll have study leave, some of them you'll be doing whatever your teachers make you do. And obviously you've got other subjects and other parts of chemistry. But just generally, I would say that we don't rush into the practice questions. You probably will be given them at school because your teachers do, because they have to give you something. And I did that working in a school. Often, you feel like you've got to give them something, and students want past paper questions, so you give them past paper questions. But actually, I would say that in terms of time, you want to spend more time on retrieval practice, which is still hard work, still effort, still lots of active stuff, not passive. Consolidation is similarly, like, sometimes there's just stuff that you need to go back over. Like, before you can test yourself, you just need to actually check your notes, make sure they're all in order, so that's what I mean by consolidation. There's going to be like a topic you didn't get and you need to go and watch a video on it, or maybe read something on a website just to really get the idea a bit better, or ask your teacher or whatever. So there's definitely going to be part of that too. And then as we go towards the end of May, that's when we are going to up the retrieval practice and the practice questions. So now it is questions, different types of questions. Short quizzes, multiple choice, blank whiteboards, asking us all those questions, and then move on to practice questions. And then really, that means you've still got 3 weeks to do past papers, because you haven't got many. You've got 7 past papers for each one, right? And then you can get practice papers as well. If you do all of the past paper questions, like the topic ones, So if you just go on physics and maths tutor and just get all of the questions and do them topic, you are going to basically, when you do the past papers, you'll have seen all the questions because you'll already done them, and you'll have done them in an easier environment. When you practice past papers, do it as a past paper, a whole thing, timed conditions, silence, no distractions, no notes. Obviously, make sure you got periodic table and all that stuff, but they should not be just done with your notes because it's not very effective. It's not preparing you for the exam. Use a weekly and daily timetable. Okay, so get an idea for what you're going to cover in a week. Like, this is what I'm going to go through this week, and then make it a bit more specific per day, but not over ambitious, right? There's no way that you can do it in terms of this is the topic I want to go through and maybe the time that you want to spend. But don't give yourself unrealistic targets like I'm going to cover all the organic chemistry today. Never going to work. Okay, let's look at exam technique. So we've got a revision plan in place. We know we should be doing retrieval practice, but of course we need to practice exam questions too. So I think this is probably going to be similar. So, oh yeah, very good question. So paper 2, 15th of May. Yeah, I'm talking mainly to A2 students, which is why I said paper 2 is in 76 days. So the majority of students that signed up are year 13. So I'm talking about the A-level paper 2. Okay. And yes, CIE do have more past papers because they have more than one exam period. So where you lose the most marks in organic chemistry, where do you think it is that you are maybe going wrong, something like you're always doing this and you don't know why you keep doing it? I know some people earlier mentioned about things that you need to watch out for that they don't see in an exam question. Reagents and mechanisms, definitely. We're going to talk about that a lot. Yeah, A-level paper 2 is the same for all the exam boards if you're doing like the major, so Edexcel, AQA, OCRA, paper 1, 2, and 3 for the A-level are all on the same days. Yeah, careless mistakes, understanding the chemistry of what's going on. Yeah, okay. And absolutely, okay, big mark essay questions as well. Nice. Okay, so what we're going to cover in this, we're going to talk about using your data booklet, which you may find an unusual thing to do, but trust me, it's useful. We're going to look at command words in exam questions and why they're important, and key terms. So reagents and conditions are definitely going to come up with that. We're going to look at synthesis and reaction pathways and some strategies for dealing with those longer synthesis questions. We're going to look at what we do with unfamiliar mechanisms too. And also analysis questions, because I know that this is a big part of it. So the infrared, mass spec, etc. Okay, now using your data booklet is, funnily enough, like something that we're not really told to do. Well, we're told to use our data booklet when we need to get the data, right? So if we're doing an infrared or NMR question, we might be looking up tables like this one. Now, again, it's not exactly the same for every exam board. So I apologize immediately if you're doing AQA, because actually you don't have a lot of clues for AQA in your exam booklet. Examiner's notes do help, yes, but you're not allowed to take examiner's notes into your exam with you. So this is actually things that are going to help you when you're in the exam. So, because if you get stressed and you're trying to remember lots and lots of things, what can really happen is mental blanks. And oh my God, there's no mental blank that I haven't seen, like amongst the student. Literally, I've had everything from forgetting what the boiling point of water is, forgetting what an alcohol functional group is. It's not because you're stupid or you've not done the revision. It's just because you're under stress. And mental blanks are normal. We all get that situation where we know the word, we can't remember it. Now, retrieval practice will reduce this. Okay, because if you get lots of mental blanks where you're like, I am familiar with this and I know I should know it, but I don't know it, as opposed to thinking I've never seen this before, then that is because you haven't practiced retrieving it enough. So your brain doesn't know it's important enough. Okay, so the one on the left, I think, is an Excel, and the one on the right is OCR. I just wanted to point them out because they've got a list of functional group names and they've got bonds next to them. So, for example, if you have forgotten, one thing that people really go blank on is carbonyls and things that contain C double bond O's. And in both of these, one of them is the infrared and one of them is the NMR peaks. What it has is, here's a list of all the functional groups with C double bond O. Obviously, it's not going to draw them all out for you, but if you've forgotten what an acid anhydride is, sometimes it is enough to just see the word and go, that's the one I was looking for. Or if you've forgotten which one out of amines and amides, like one of them has a C double bond O and one of them doesn't, this list tells you that amides have a C double bond O. Or even, we forget nitrogen sometimes have there's lots of things involving nitrogen. There's your NO2s, so your nitro, your nitrile, your amines, and your amides. Again, this is giving you clues. Not true for every single one. So I apologize if you don't have that, but get to know your data book before you go into the exam. It's the same every year. Okay, so there are useful things in there. They don't always tell you when to look at it, but you can look at it whenever you like, and it is really helpful. Okay, now let's talk about command words. So one of these command words, someone said about getting wrong reagents and conditions. And again, it's not always because we don't remember it. It can be exam technique. So a reagent is part of the overall equation. It's not a catalyst because that's part of the conditions, although sometimes we might kind of group them together. Oxidizing agents are reagents because we have to put them in there to get the reaction to work. Reducing agents are reagents. And then maybe there's lots and lots of other things, electrophiles, nucleophiles, etc. One thing to be careful though for is that when I just said, oh, for example, a nucleophile could be a reagent. If, for example, I want to react something and it's a hydroxide ion behaving as a nucleophile, some examples are very, very specific that your reagent is not just OH minus or hydroxide, but that it is a full compound. Okay, so think of a reagent as something that is part of the overall reaction, so gets used up, and is something that I could go down to the prep room and ask my technician to give me a bottle of that. Okay, so what I can't do is I can't go, can you give me a bottle of cyanide? Because she's going to want to know what type of cyanide. Hydrogen cyanide, potassium cyanide, sodium cyanide. If in doubt, stick a sodium or potassium in the front and you're generally good to go. Okay, so dichromate, I want potassium dichromate or sodium dichromate. It's the dichromate ion that's doing the thing, the actual reacting. But I need to have something in front. It's always group 1 because group 1 is soluble. That's the only reason. Okay. Absolutely, acidified is also part of that as well. So all our oxidizing agents need to be acidified. But if I just say the word acidified, sometimes that isn't enough for the reagent. I might have to name the acid, like sulfuric acid. Very good question. Do we need to add aqueous symbols? You're going to have to take some clues, I think, sometimes from the question. I would say usually not, but there are some cases where we might have to be a bit more specific. So if I know it has to be a solid, then I'm going to need to say that. So like drying agents have to be solids, solid calcium chloride, for example. If it's an acid, and I would generally say whether it's concentrated or dilute. But for dichromate, I don't normally put aqueous to say that it's aqueous most of the time. And in fact, I would avoid adding the word aqueous because of the conditions. So temperature is obviously part of it. Temperature is very rare. Usually it's just heat. If it's heat, it's usually under reflux, because if you don't heat stuff that's organic under reflux, it's gone. It's going to evaporate too quickly. Just be aware that a few reactions need a specific temperature. Usually it's the gas reactions with a catalyst where you have to know the catalyst as well, where you might also need to know a pressure. Does depend a bit on your exam board, but temperature, usually it's just heat. Catalyst, there's never a mark for saying in the presence of a catalyst, okay? You've got to name your catalysts. If it has a catalyst, you've got to know what the catalyst is. We often put that in with reagents, and usually it's fine because the question normally says reagents and conditions, so it doesn't matter whether you put the catalyst all together with everything else. Obviously, acid is a very common catalyst, but it's not always a catalyst, so sometimes it's actually part of the reaction. And aluminium chloride for your benzene reaction. If you've got stuff happening in gas state, then the catalyst is usually a solid, like nickel or platinum. Okay, so that's how we know when we're using a solid catalyst. Solvent is a really neglected area that students don't remember or think about. Okay, there are 3 main solvents. Obviously water. Then you've got ethanol. And then you've got ether, or sometimes called dry ether. So water, actually not that common, okay? Basically, if you're making something containing oxygen or with an OH group, then water is generally fine. But if you want to make something that doesn't have an OH group in it or doesn't have oxygen in it, so if you want to make a nitrile or an amine or some other functional group like that, then I'm not going to use water. And that's because water is a really good nucleophile and it tends to react. And water also reacts with other things. Water reacts with the catalyst that we use for benzene reactions. Ethanol's good for, yes, it finishes at about 12:45, although some of that would be question time. So the ethanol is good for haloalkanes. It helps dissolve them, but also it doesn't react with them. Okay, and then ether is when we're using things that are super reactive, like acyl chlorides, or aluminium chloride when we're doing benzene. So lithium aluminium hydride, if you do that for reduction. So lots of things use ether, and they're dry ether because basically they can't have any OH groups. No OH groups from water, no OH groups from ethanol. OH groups are super reactive. That's why we use different solvents. Pressure, as I've already said, like sometimes for a gas reaction, you've got to know the pressure, but most of the time you don't. Okay, some examples are a bit fussy. Oh yeah, so dry. Yeah, I threw that in, didn't I? So water's the only liquid in chemistry that's actually wet, considered wet. Okay, so you know, if you spill like nail polish remover on your skin, it doesn't feel like water, it evaporates super quickly. So that's like a dry. And when we use the word dry cleaning, that means cleaning clothes. It doesn't mean no liquid, it means no water. So like, you might clean like a suit jacket with a solvent. That is not water. When we say dry, it just means that we've really made sure there is literally not a drop of water in there. So for example, like acyl chlorides, your COCl, they are super, super reactive. You can't even wash your flask with water before you use those because they will react with the water that's still on the side of the flask. So that's what we mean with those. Name, formula, identify. So identify means you can say what you like. so long as it's correct. Name means please do name it. Sodium hydroxide, etc. Potassium dichromate. Formula means exactly that. It's rare that they ask for a formula for a reagent, but they may well do. And again, a formula is a whole compound, okay? A formula is not OH minus or CN minus. It is NaCN or NaOH. Okay. And I've already said this, reagents should be whole compounds, so that's cool. So reagents and conditions, once you've learned them, don't miss the marks just because you didn't follow the instructions in the question. Chemical tests, there's a lot of those as well, right? Tests for different functional groups. So again, once we've learned them, we don't want to miss stupid marks. And that's what this part of this thing is about, is do not lose the silly marks that were just like, they're what I would call like the obvious marks. And students are like, well, that was obvious. I didn't know I needed to write that. So obviously, you've got to say what you add for a chemical test, including extra stuff. So absolutely, if you're using dichromate, you've got to say with acid. Otherwise, it won't work. You might also have to say that you have to heat some of them. Okay, so if I'm using dichromate in a chemical test, I am going to need to warm it up and it's got to be acidified. If I'm adding some sodium carbonate to an acid, it's good then to say whether it's aqueous. So for chemical tests, I would try to say what state it's in, and it's usually aqueous because chemical tests are meant to be quick, easy things. It's not like synthesis. They are designed to be quick, easy things that give you quick, easy results to test for something so that I don't have to go and put it in an infrared or something like that. What you see needs to be a thing that you actually see. So if I see bubbles, say bubbles. There's no point trying to be fancy by saying effervescence unless you really enjoy spelling it. There's also not going to be necessarily marks for saying things like gas given off, because that's not something you see. You don't see gas. You see bubbles of gas in a solution. Color change. Sometimes you need two colors for one mark. Orange to green, for example. Blue to brick red, not or orange to colorless for the bromine water test. So make sure that you actually get that the right way around. Oh, a nice indicator question. Okay, so I get confused with methyl orange or phenolphthalein when writing the order. I think that's just practice and also just practicing it all the way around. So if you make yourself some flashcards and it's like, what color does it go? Acid to alkali, alkali to acid, methyl orange, phenolphthalein. Practice it a few times and you will definitely get there. Also, make sure to check your data book for that because some examples actually give you the colors of indicators and all you've got to do is apply them to the situation that you've got, like whether you're starting acid, alkali, alkali to acid. Comparison. So this is what some people forget about as well is, for example, if I say a test, can you give me a test that will show the difference between this aldehyde and this ketone? And you go, oh, I know what we're going to do here. I'm going to add Tollens reagent. It's going to give a silver mirror. Okay, but what happens when I add it to a ketone? Compare. Okay, say the aldehyde gives a silver mirror. The ketone, no reaction or no change, whichever you like. No change is actually better because it means there might have been a reaction, but you don't see anything. Same, if I add bromine water to an alkane, nothing happens. And if I add it to an alkene, it goes colorless. So you are doing the comparison too. Sometimes it's like 3 marks, one for the test, but then also specifically saying what happens in the different circumstances. Okay. More about command words. How many types of reaction? Just organic. How many organic types of reaction do we think there actually are? Like, when you have to label things like nucleophilic addition or free radical substitution. How many do you think you've learned over the course of your A level? Just give me a rough ball. I actually misread that. I thought it said 678, but it actually said about 6 or 8 or 7 to 8. Okay. Nice. Okay. Oh, we're going up. No one's gone above 10. Let's see how many I've got here. Okay. We started with alkanes, usually year 12. We went on to alkenes. We did electrophilic addition. We carbonyls, no, then we did haloalkanes, nucleophilic substitution. Then we did our carbonyl compounds. We did addition. We did our benzene. So these are all the curly arrow ones. Most of us also need to know elimination reactions or dehydration and curly arrows. So these are not necessarily all ones that we have mechanisms. Free radical absolutely is a mechanism. It's not a curly arrow mechanism, but it's got steps. Oh, such a great question. Thanks for asking that. Difference between mechanism and type of reaction. The type of reaction is what happens to the organic molecule. What do you do to it? Okay, so for example, dehydration is removal of water from a molecule to make a double bond, or elimination is just removal of something else. Substitution is I take a group off like a Cl and I put something else on, and addition is I add something across a double bond. And then the other words, the free radical, electrophile, nucleophile, that is how the mechanism kicks off, how it starts. So is it about a lone pair being donated to a carbon? Is it about a double bond electron pair being donated to another species? So like, where do the arrows start and move? Is it about breaking a bond to make free radicals? So it's just about like, what is it that causes the reaction to get going in the first place? That's my mechanism. Where do the electrons go? What order do they happen in? Which bond breaks first? That's a mechanism. And then substitution, addition, elimination, etc. They are just basically what happens overall. So there are other things which we don't draw mechanisms for, but we do need to know what happens overall, like oxidation, reduction. So oxidation can be adding oxygen or removing hydrogen, and reduction is adding hydrogen or removing oxygen. They both work. Condensation, which in AQA is called addition elimination. Sometimes we call it esterification, but that's not actually a type of reaction. That's just I'm making an ester. That's cheating. So if it says what type of reaction it is, don't put esterification. Okay. Also for benzene reactions, don't put type of reaction is Friedel-Crafts. That's just the names of the guys that invented it. Call it electrophilic substitution because it's like what type of mechanism. Hydrolysis, opposite of condensation. Addition and condensation, polymerization. I chuck those in. They are just types of reaction, but they're applied specifically to polymerization. And I think sometimes people don't realize there's only two types of polymerization, and that will make it a little bit easier. Well, that's another great question. Is the end product necessary to draw? I'm not sure about that indicator question, Abby, so I'm going to leave it because without seeing the question, I think I wouldn't be able to get it. Is the end product, let's talk about drawing stuff. So mechanisms, yeah, often you don't actually get a mark for drawing the end product, weirdly. But what I do want to talk about is when we lose marks for drawing organic compounds in the wrong way, and also when we sometimes lose marks because we try to draw organic compounds in the way that we think we're supposed to, and then actually just make it harder for ourselves. So importantly, if a question says displayed formula, you have got to show everything. Okay, so actually, this doesn't come up often, 1 or 2 times. And they are testing that you understand what a displayed formula is, that it is showing every single one of the bonds. So the common ones that people miss are, of course, your OH bond. Also, when we get into nitriles, people miss this. So sometimes they want you to do the CN bond. They want you to know that it's a triple bond and show that. And the other thing is you do this beautiful displayed formula with a functional group, and then you stick a CH3 instead of actually showing every single C and H. I've got a thing on polymer. I have a video on polymer repeat units that might help you. So skeletal formulae, again, that is testing that you know how to do skeletal formulae. The most common thing there is missing carbons, or extra carbons. So the best thing to remember is the number of lines is not the number of carbons. So if I go 1, 2, 3, 4 lines, that's 5 carbons, right? Because the ends are carbons. And if I want to then add something to it, like a chlorine, I will need another bond to add a chlorine. And that's the thing that people forget with skeletal, is they just sort of add an atom next to it. You have to show all the bonds still with skeletal except the CH bonds. But if a question just says draw the structure or draw the mechanism, unless they really point it out, you can do any kind of mix of structural, skeletal, so long as it's clear and accurate. So if your comfort zone is displayed, that's okay, but you should practice when you're doing retrieval practice other types of formulae. But certainly for a mechanism, I know some people would rather, I would always display the bonds. There is no skeletal formula of methane. You would simply write CH4. You can't do a skeletal formula for methane because it'd be a dot, and that's not a formula. So even if it starts the mechanism, sometimes you get a bit of a mechanism in one type of drawing. You don't have to feel like you have to follow it and carry on drawing it. So I've seen mechanisms that start skeletal. It's perfectly acceptable to draw the middle part of the mechanism non-skeletal. Like if you want to write CH3 instead and make it clearer to you where the carbons are, sometimes that helps. For a mechanism, you would definitely need to show important bits like bonds with dipoles. If you're going to break a bond, you've got to show that bond, right? You can't do a curly arrow from a bond if you haven't actually drawn the bond in. So that's important. But you don't have to show the whole thing. Other things about drawing organic compounds. So bond angles. When does it matter? We don't always have to show everything in 3D. That would be really confusing. But there are a few occasions where bond angles matter and we need to be a little bit more careful. Hopefully, EZ isomers. You can't draw EZ isomers without showing the sort of what I call the 4 corners of your alkene. So you've got your double bond, your 2 carbons, you've got top right, top left, bottom right, bottom left, because then you can compare where your different groups are. Also, other type of stereoisomers, optical isomers. I also just want to point out at this point that when a question says stereoisomer, that these are both types of stereoisomer, because often, again, our brain gets used to one thing, like if I've just been doing a load of stuff on alkenes, and we forget that there's 2 examples of it. So if a question says stereoisomers, make sure you think, okay, I'm looking for EZ and I'm looking for optical. It could be either or both in one molecule, because we could have complicated things. And if you're doing transition metals, same with complexes, right? It could be cis trans or optical. You just need to make sure that you look for both types of isomer. And if it just says isomer, could be structural, could be all sorts. Hydrogen bonding, bond angles are usually important for hydrogen bonding too. So if I'm showing, and hydrogen bonding comes up loads in organic chemistry, not just in the sort of biology side, like the DNA and the amino acid stuff, but also just boiling points, molecules bonding together. So when I say the angle is important, it is this angle around the little hydrogen. That is, the hydrogen's almost kind of like being shared between the 2 oxygens, and that's 180 usually. EZ is almost the same as cis trans, yes. Cis trans only applies when I've got 2 hydrogens, like 1 on each carbon, which I have here. EZ is for everything else, okay? So I could have like 4 completely different things around my double bond, and that would be EZ isomers. That's why we've got the different names. But yes, you can just remember it as cis trans. So if I'm writing an equation, we said sometimes we've got to write like a balanced equation. Generally, you can choose whichever formula you want, okay? By which I mean, skeletal. or displayed. But what you can't do is make it such a simple formula that it's not clear what the product is. So if I see C3H7Br, so this is an alkene, I've got C3H6. If I see the formula C3H7Br, to me, that looks like the bromine is on the first carbon, and that's like a propyl group. In the same way that if you imagine I was to write C3H7NH2, I would think of that as propylamine. Okay, I wouldn't think the NH2 was in the middle of the molecule. I'd think it was at the end. So it's ambiguous at best. At best, it could be 1 bromopropane or 2 bromopropane. And if I was guessing, like most students would, most students would look at that and go, that's 1 bromopropane. But in this, we're adding HBr to an alkene that is not symmetrical. And for a couple of exam boards, you are meant to know that the bromine goes in the middle. That's the major product. There should usually be clues in the question, by the way, that would say things like major product, so that you don't have a choice of which one to draw. Or they might say you can show either. But if you are trying to show the formation of the major product, you need at the least a structural formula or skeletal so that I can see what a bromine is, that it's on the second carbon, because that's where the positive carbocation forms in the middle of the mechanism. So basically, if you draw the formula of your organic molecule and you want to use structural, which actually not many people do, and you don't have to, okay? So there's nothing wrong with showing this displayed, and then you will usually get it more correct. But again, so a substitution reaction between sodium hydroxide and 2-bromobutane, again, that's not good enough. I cannot be writing C4H7Br because it's not 2-bromobutane. My question wants me to show 2-bromo, and the absolute minimal way that I can show that is with a structural formula. I could probably do C2H5 on the right-hand side instead of CH2, CH3. If you are really struggling and you commonly miss out hydrogens, or get the wrong number of hydrogens, then draw it out instead, because it's quite easy to get the right number if you show a displayed formula. And you can see there is a Br and an H. But you've got time to practice. So practice doing structural because it's a time saver. There is no one thing for structural formula, okay? There's no one definition. It's not like skeletal where there's a very strict way to do it, or displayed where you have to show every bond. So again, there is nothing wrong with going CH3 and then going, oh, do you know what? I'm not really sure how to show that, so I'm just going to do that. And then that. That is also a perfectly good structural formula for 2-bromobutane, because I'm showing where everything's attached. So don't feel like you need to use brackets and put everything left to right. It's not necessary. Just make sure your order of your bonds is right. Okay, so we go CH3. If I'm doing a structure like that, you can also do H3C. That was the next thing I was going to say. And certainly if I'm drawing a structure, maybe doing the shape, maybe doing something like EZ isomers or optical, then I would definitely consider doing it like that. Certainly if I'm doing something with that, and I could do a C2H5 as well. But if I was doing a linear equation where I was writing CH3, CHBr, we tend to do it like that. For multiple choice, look out for them writing it the other way around, because it can really throw you. So one thing to practice is writing organic molecules lots of different ways. Like take one molecule and practice showing it different ways, upside down, right to left, left to right, sideways on. Sometimes we draw a molecule down the page. It totally messes with people's heads. Again, with equations, make sure you know what equation they're asking for. if we number carbons from the other end. Oh, absolutely. Yeah. So if I put my bromine, that's why I said about left to right and right to left. Obviously, molecules don't have a left to right. So if my Br is on the second carbon from the right instead of second carbon from the left, that's fine. It's still on the second carbon. Which equation do they want? So writing an equation for the formation of the electrophile is not the same as write an overall reaction. Or in this, so, you know, for this, I would be doing something with my aluminium chloride. And how do I make a Cl plus? So formation of the electrophile means I'm making my positively charged chlorine, whereas overall, then that case, I don't use the aluminium chloride in the overall equation, because in the overall equation, aluminium chloride is a catalyst, so it doesn't go in the overall equation. And so that would just simply be benzene. I'm adding Cl2, but only one of the chlorines is a substitution reaction. And so that would be my overall. Your overall is usually just two things added together makes two things, or maybe two things as one if it's addition. Doesn't usually have lots and lots of things involved. We could do a similar one for an alkane and chlorine, and we don't see any chlorine radicals in that. We're just, again, reacting with Cl2 and making HCl. So that was my point about those are both substitution. They'll have both the same overall type of equation, but they have completely different mechanisms as to how they work. And so for free radical, we could have an overall reaction, or we could just have a step like making the chlorine radicals, initiation or propagation, termination. Okay, how are we doing for time? We've got time to just look at some synthesis and analysis questions. Okay, so one thing we said with synthesis is retrieval practice is going to really help in terms of looking at all your different functional groups, learning all those reagents and conditions. But the other thing we said was to think about how you make a functional group rather than always thinking about going from A to B, to think about going from B to A. This is mostly year 13 hours, yes. So, although there is synthesis in year 12 as well. So if I was to look at this one, rather than going, oh, how do I start with benzene and get, yes, there will be some useful stuff as well when we do in about 10 minutes when we look at the last bit as well. Or you can just drop it back into the recording if you want to. So the thing that I would look at is not how do I start from benzene and get all the way down to there, is I would look at, oh, look, I've made an alkene. How do I make an alkene? And I would be thinking of what are the reactions I know for making an alkene? Well, one of the reactions I know is elimination from a bromoalkane. So maybe I could work out that B has a bromine on it, because then I can get rid of the bromine and an H. So maybe there's a Br there. And then I can think, well, how do I add that? Well, anything I add to a bromine, I just need to chop it off and add a bromine and or a chlorine or something like that, and an acyl chloride catalyst. So working backwards is a lot better than just, especially when you've got more than one step. Try to think about in your retrieval practice, when you're practicing, how do I make an alkene? How do I make an alcohol? How do I make a carboxylic acid? How do I make an amine? Don't always start from them and go forward. Definitely look out for extra carbon atoms. Now, this obviously has extra carbon atoms compared to the start. There are two main ways of adding two. Sorry, there's three depending on your exam board. You've got adding carbon to benzene, which is your Friedel-Crafts, having a chlorine attached using AlCl3. You've got cyanide, which can be nucleophilic addition or substitution. So you've got a couple of functional groups that react with Cn. If you do Edexcel, you've also got Grignard's reagents, but that's much less common. So if you see something start with 2 carbons and end with 3, that's a huge clue that you need to get involved. So do a separate bit of revision. It's sort of added into your synthesis. How do I add a carbon on? Because that's super important. It often comes up. If you see a functional group move, it did not move. So what I mean by that is there is no way that you can just make a bromine hop from one carbon to another. And also there is an intermediate in between. So if it looks like a functional group has shifted, like a Br or an OH, you had to go through a double bond because there's no other way that you could get something to move into the middle of a molecule. And that works because we've got our addition, and we talked about this earlier, the bromine goes in the middle. And so you have clues like that. Think about, okay, I'm probably going to have to eliminate from the molecule and then add back onto it. I cannot just, hop a group over. You can't just break a bromine off and attach it to something else where there wasn't anything to attach it to. So we sometimes get these reaction pathways as well. Specimen papers are harder than past papers. I would agree, yes. Sometimes specimen papers are actually a bit minimal, like they're not always that hard. What I will agree with specimen papers to point out for, they're useful practice. The mark schemes for specimen papers are not very good because no one sat them. And normally mark schemes go through this process of change and improvement during the marking period. So when me or another teacher is marking and we get a question we're not sure, we got an answer and we're like, oh, I think this is actually valid, but it's not on the mark scheme. So we bring it up and then it gets added. And so there are extra options. So when you see all the things that say allow this, don't allow this, that's through the discussion of the people marking the paper. And because the specimen papers didn't have that, they haven't got as much detail in the mark scheme. So they're not as useful for that reason. Reaction pathways, they can be a bit heavy. The reason I wanted to point this out is just to watch out for multiple functional groups in one molecule. That's how we do A-level now. So, and even to some extent, AS and Year 12 as well. I will send the recording. I won't send the PowerPoint, but I will send the recording. And then the reactions. So when it says reactions involving 2-hydroxybutanoic acid, instead what I'm going to do is switch on in my head. Right, there are two things here. There's an alcohol and a carboxylic acid. What do I know about the different reactions of each of those functional groups? Rather than trying to look at the whole molecule. We're going to ignore the CH3, CH2 bit because that does nothing. And we're just going to look at, oh, okay, actually, how do I get to a carboxylic acid? So there are two things there where I'm going that way, or how do I get to an alcohol? And then we can start to link it together. So identifying separate functional groups, and then using all of that retrieval practice we've done in terms of what do I know that these reactions do, or how do I make an alcohol? How do I make a carboxylic acid? So for example, the one going from left to right is actually going from CN to COOH. So that is hydrolysis of a nitrile. The one going up, now I can't make a carboxylic acid using sodium borohydride. And don't worry if you don't recognize that, by the way, because it's not in every exam board. But I can start with a C double bond O and reduce it. NaBH4, by the way, is about the same as LiAlH4 if you use a different reagent. And then on the other side, it's basically I've got an acid reacting with an alcohol or an alcohol reacting with an acid. So both of the top boxes are about making an ester, but they're just about making an ester using different parts of the molecule. So be switched on to different functional groups. If you see loads of stuff going on, again, just work backwards and do it like a little jigsaw puzzle. Okay, so there are loads and loads of things here. If we haven't done that, okay, that was a good question. So I'll go back to the previous one. How would you know which one it is if it has multiple functioning groups? Because when you do your retrieval practice, you are going to sit down and you're going to write out carboxylic acids and you're going to go, what do they do? Now, actually, carboxylic acids don't do much. They make esters. That's it. And then, so basically, if I've got an arrow coming away from a carboxylic acid, it's going to react with alcohol to make ester. That is the only thing that carboxylic acids do. Then you might think, how do I make a carboxylic acid? And one of the ways, oh yeah, you can make acyl chlorides. Again, that is exam board specific. Some people don't have to know how to make an acyl chloride. And then you would say, what are all the ways I know how to make a carboxylic acid? One of them is oxidation of an alcohol. One of them is hydrolysis of a nitrile. Again, that's exam board specific. And then you would be like, okay, again, with the alcohols, what reactions do alcohols do? They do oxidation, they make esters. And then how do I make an alcohol? I can make it from a bromoalkane, or I can make it from reduction of an aldehyde or ketone. So by having all of those in your toolkit, you will be able to quicker match. The other thing you should do is match the mechanism, the type of reaction, to the functional group. So like alkenes, always electrophilic addition. That is all they do. And so when you get, again, a big complicated stuff, you will then be right. Dehydration is the only, how do you know if the bottom is trying to make the alcohol? Because what they react with. Because you can't make a carboxylic acid using NaBH4 because it's a reducing agent, and carboxylic acids are like super oxidized. So you can't therefore reduce to make it, but you can go from a double bond A to an OH. So in this one, again, I would just look at the different things like dehydration. Dehydration means removing water. Well, I can't involve CN in that because it doesn't have any water in it. So I'd have to take off an OH and an H, which leaves me with a double bond because you can't take things away. You have to make a double bond to do that. Just like if you add something, you have to add across a double bond. Once I've got a double bond, it makes it a bit easier to see that I'm adding HCl across it. And then there's all kinds of things going on with reagent 4 and concentrated H2SO4. But that is because it is, in fact, just making, what is it doing? Oh, no, it's turning the CN into, like, that's a very bad one, actually, because I've just realized adding the HCN would make a weird compound, HCl. So what I want to point out there is just pick out all the clues in the question. And don't panic if you don't know every single one, and work backwards. So again, if I've got H2SO4 as like a catalyst and a reagent, and remember, reagent means something that actually reacts, and reagent can be an organic thing. Okay, so I would look at this methyl methacrylate and go, oh my goodness, well, I'm pretty sure that compound A has got a double bond because I removed water. So I removed an H and an OH and made a double bond. It doesn't matter which side because it'd be the same. And then this is an ester here. So I know that to make an ester, I have to have like a carboxylic acid and an alcohol. So I'll be like, well, okay, well, compound B just must be this then. And reagent 4 must be this alcohol here, which would be methanol. So I just like try to cut bonds, see where the bonds would form and see where they would break. It's not easy. I'm not saying that, you're going to get 100% on every single question. Some of them are super difficult, but having that retrieval practice will help as well. Just going to look at mechanisms because time is ticking. Just some tips for mechanisms, really. So polar bonds, things that happen a lot. So things that you can predict, yeah, that's likely. Would be polar bonds breaking. So, a CBr is a delta minus, a delta plus. It always breaks that way in terms of I'm just moving the electrons towards the thing that already broke. And that can happen with double bonds as well. And double bonds often break in chemical reactions. And often we have a hydrogen, an H plus, being lost. And whenever we lose an H plus, we always have the arrow therefore going from the bond with the hydrogen to something else, never to the H, because if I did the arrow to the H, that would mean I would be losing H minus. And that's a very typical wrong arrow in a mechanism question. So hydrogen ions get lost and gained all the time. Double bonds become single. Polar bonds broke. Those are things that we can really predict happen. And occasionally we make double bonds from single bonds as well. What does not happen? Carbon-carbon bonds do not break. Never. Really? Okay. You never get a C just coming off another C. That does not happen. That's incredibly difficult. You can do it in cracking reactions, but that's high pressure, high temperature catalyst, not normal chemical reactions, and certainly not mechanisms that we're drawing. Okay. It happens in radical reactions because anything happens in radicals. We don't even make carbon-carbon bonds very often. Double bonds break completely? No. So if you've got a C double bond O, at the end of the reaction, it will either be a C single bond O or it'll be back to a C double bond O. It will never completely break off the O. If you have an alkene, you would never completely break apart the carbons. And you never have arrows going like this or arrows going like this. So curly arrows, they kind of follow each other through a mechanism. A pair of electrons comes in, a pair goes out, a pair goes out. Because otherwise, you can imagine you can't just be putting 4 electrons into one space where they weren't before. It's just too weird. Okay, like why would you suddenly end up with like 4 more electrons than you started with? So generally, electrons go in and go out. So if you had something like this crazy beast and you had to draw, so we've never seen this mechanism before, unless you've done this particular question. And it says the first step, and all we want to do is draw the product. So I can follow it around. You can see the arrows are doing their little follow me round thing. I can see the double bond has broken because I moved a pair of electrons away from it. So that O there has to be joined to one of the carbons. Now, because this arrow is going into the right-hand side, that means that I would need to be drawing that O up there. It doesn't matter if your bonds are a bit wonky, like mine. Then, so what I've done is I've shown this arrow shows a new bond being made. Then I can see the double bond in between those 2 oxygens is broken, has gone O. There was a plus here, but I moved a pair of electrons to it, so it's not a plus anymore. And then this is still attached because there was no arrow here, so nothing happened there, nothing changed. And then the last O joined to this carbon here. So basically what I've done is join 3 oxygens together. I've basically just added across a double bond. That's all we've done. That is the same as if the arrow went to an H and the Br broke, and then the Br minus went onto the other carbon, and then what you end up with is basically, the only difference here is that this thing stayed connected instead of like splitting into 2 separate atoms because it had a double bond in it. There's no overall charge, and that's because I started with a plus and a minus, and now I don't have like, so therefore there's like no overall charge, and there's still no overall charge. So I'm not saying it's easy, but I'm saying there's ways that we can follow the arrows. And then this one, it says draw 2 arrows just to make the mechanism complete. So I'm not going to add anything to the first step because that would be a strange thing to do because there's already 2 things happening. So I've made a bond, which I can see here. That's the NC bond I've made. And then I've broken this CO bond to make it single. So I can see that that's happened. And then there is a whole load of stuff going on. And there's a really weird, it's probably quite hard for you to see, OH, CH2, CH2, NH3. So I would basically then be thinking, well, that's like that, but without an H. And one of the things we said that happens all the time is H gets removed as H+. So I could simply do this and I would have finished. my whole reaction. Just by knowing that quite often amines are bases, they remove H+. That happens very commonly. So the more practice you do, the better on that one. Okay. Oh my goodness. I've talked a bit too much. I do apologize, but that's because I am probably answering your questions as I go along. So hopefully we won't have too many, but I'll stick around. Infrared. What I wanted to point out here, yes, you have a data book. And I did say, look at your data book, use your data book, etc. But I mean, don't rely on it and don't be looking like, it's like when I say use the periodic table. You don't have to know all the elements that are on the periodic table. But if I ask you to find magnesium, I would really hope that a second year A-level chemistry student or even a first year one would know it's in group 2 and not be like just all over the place. The same for infrared. If we do our retrieval prompts and be like, okay, have a good idea about where OH and CO are. So OH is always like higher than 3000. So this little peak here is a CH. This has definitely got an OH, and this is a CA. This is like a big fat OH, which is probably a carboxylic acid because it's really wide. But this ain't an OH, okay? So that's why I wanted to show you the spectra side by side, is for you to realize it looks different. It's pointy. It's not broad and wide and smooth like an OH peak. And it is, you can really clearly see that it's just below 3000 and not above. Okay, so don't mistake a CH for an OH. And then when it comes to C double bond O, don't mistake a CC, which is this little guy, for a CO, which is this one, because you can see they're really in a very similar part of. Are all of those carboxylic acids? No, I reckon some of the ones on the left are probably just alcohols. If it's a carboxylic acid, top right is a good example. It really spreads out over the 3000 and goes a lot wider. It's always a little bit tricky to tell, and you should look for other information in the question as well. Don't ever use just the infrared value, like the wave number, to tell you if an OH is a carboxylic acid. Basically, you'll know because you can look for a C double bond O. And that's how I know that, in fact, the ones on the left are not carboxylic acids because they don't have a C double bond O. Actually, the one at the bottom does. So how I know is that C double bond O is a lot deeper usually. It's a lot bigger of a peak. C double bond C can be a very small peak. C double bond O is a very strong absorber of infrared. That's why carbon dioxide is a really good greenhouse gas. As for that one, 1560, no, that is actually a CC again. You can see it's a lot smaller. So look for bonds together. If you're trying to decide if something is a carboxylic acid, proper little sneaky thing they love to do these days is, even worse than that, to have an alcohol and a C double bond O in the same molecule, but they're not actually part of the same functional group. So like an alcohol at one end and a C double bond O. That's when you need to use your combined techniques and actually look at things like NMR and mass spec to help you out. So yes, the top right is definitely a carboxylic acid because that is 1700. You can see it's a little bit higher than 1700, whereas the CC peaks are just before 1700. They're like 1650. You will have the table. You don't have to learn the numbers, but it's good to just notice this very slight distinction on either side of those lines. That will help. But most of the time, we're going to have this alongside all the other stuff, so we put it together. If we're doing mass spec and we've got lots of other information, then the most important thing is to get the molecular ion peak. So for this one, it's an empirical formula question. So I do my calculations and I get C3H6O. the very first thing I'm going to do is check on the mass spec and see whether that is C3H6O or whether it's C6H12O2, for example. So I have a look and it's 58, which means it is C3H6O. Don't have to do the math. And then I would check the other one. It's also 58. You may be looking at it and thinking that looks like 59, but you can't make an odd number with carbon, hydrogen, and oxygen. So it is that one. They're both the same, therefore, and then basically there's only two possible structures. So it might look like, C3H6O, what am I supposed to do with that? Like, that could be anything. No, it can't, because there's only certain ways they can join together. Spot. How did I get the molecular formula? Just doing empirical formula. Just doing 62 over 12 and 10 over 1 and 27 over 16. So practice your empirical formula calculations, and they're quite easy. Once I did that, the other thing that I know is that is a 1:2 ratio of hydrogens, which means it contains a double bond. And it says they're carbonyls, which means C double bond O. And so basically, I've only got two options, which is propionate, or I've just mixed up my formulae there, propanol. And then I can just look for one peak which doesn't work. I do know 2 electrons can be knocked off. Yeah, so in mass spec, you could have 2 electrons knocked off. It will just give you a peak of half the molecular ion peak though, which wouldn't be very helpful. So in this case, that would be 25, 29. The thing is, you can get a peak at 29 anyway. And the probability of 2 electrons getting knocked off is tiny. So the peak that you get from having 2 electrons knocked off is so small that you would never, ever see them. So I wouldn't worry about that one. Because all these tall peaks are common. And the common peaks will be, it's more likely that 1 electron gets knocked off, not 2. Okay. All we've got to do is look for something that you can get with one molecule that you can't get with another. And actually, the easiest thing is to just look at the bonds that you can break. So 12 plus 16 plus 1 is 29. And then the other one would be 29. So whereas this peak, this one cannot make 29. All I can do is take off 15. I can make 28 if I take off 2 lots of 15. There's no way to do it. So when you're doing the mass spec, my other suggestion is to redraw the molecule like this. 15, 12, 16, 15. Just makes your maths a bit easier. We're not interested in knocking off a hydrogen. Yeah, of course you can knock off a hydrogen, but what's that going to tell you? It's going to give you a peak at 57, and it's going to give you no information about the molecule whatsoever. So there's no point looking for that peak. But if I look at that molecule, I can see it cannot make 29. And if we zoom in, so great question about the 2 electrons being knocked off. There is a teeny, weeny, tiny peak at 29, probably due to 2 electrons being knocked off. But it's definitely not worthwhile enough to mean that it's that isomer. Whereas there is a huge peak here, and look at the difference between them. The difference is 15 because either of these 2 bonds can be broken. That's very likely, and it means that I'm very likely to make a peak, which is 58 minus 15, which is going to be 35 instead. Don't worry about the 2 electrons being knocked off. It depends on what examples you do. That's more likely to be mentioned with something like AQA, where they talk a lot more about how the molecules are ionized. Whereas other examples don't really ask you very much about how the mass spec works. So yeah, don't panic. And then if we go to NMR, I'm going to sort of whiz through this one a bit quicker. Just think about the order in which you look at things. Number of peaks is most important because actually when you draw isomers, usually you can work out whether things are symmetrical. Peak area, how many hydrogens are on the peak. Lots of people don't mention that when they're actually talking about why. So the fact that one of those peaks is 3 hydrogens and one is 6, that's huge. That tells me, because you can't get 6 hydrogens on one carbon. So that means there are 6 hydrogens in the same environment, 2 CH3 groups, either symmetry or they're attached to the same carbon. Look for splitting, obviously, but that's like that's the third thing I'd be looking for. So the area is just how many. So it will have numbers next to it, like 1, 3, and 6. I would check how many hydrogens there are in the molecule as well and make sure that they're the actual number. And then chemical shift. That's the last thing I would look at. So where it is in terms of on the bottom axis, that's the last thing I would look at, unless there's something super obvious like an OH. Most of the chemical shifts are in quite a small area between 1 and 4 for hydrogens. So there's no point. Don't be sitting looking at your data book when there's way more clues. For example, this says it has 2 carbonyl groups. So I've got loads of clues about this molecule without having to go any further. And I'm really conscious of time, so I'm actually not going to go through the last 10 more bits. I'm just going to wrap up. And just, remind you, so if you signed up and you said, yes, please, then you're on my mailing list. So that means that you'll get my weekly email. I don't send them out weekly over Easter, but during term time, retrieval practice quizzes, which you can also find the past examples on my website. There's one every week pretty much in term time for year 12 and year 13, which means there's loads, and they are a really useful, random, quick way to revise because they just give you 10 questions. Now that you're getting towards the end, then therefore there you will be, they're not all been put up now. So when you're on the email list, you'll get them every week, and then about every month I put them all up. 101 revision activities. That's another thing that there's actually 202 because there's one set for AS and one for the A2 stuff. Multiple choice questions. Definitely also, so I'm going to be sending out an email which also has a summary of extra little revision resources, including the revision planner. I've got a whole set of 50 multiple choice questions, which each one of them has got a little walkthrough. So that might be useful for you to practice your multiple choice. OCRA is now sold out. EdXL is sold out. If you're in AQA and you're quick, I am running Easter holiday boot camps starting on next Monday to Wednesday. And they are in very small groups. So if you wanted some really detailed work, check that out because I don't have any spaces in OCR or EdXL, and it's just AQA now. Also, same for the revision classes. So like the master classes, I've been doing them all year. One thing you can do very cheaply, 50 quid is access 20, more than 20 hours. I think it's 23 hours of really detailed master classes along with practice questions and everything else. So it's like meant to be a whole revision package. And then I have also got extended response. So some people talked about 6 markers. I've got 6 marker practice booklets for the 3 main exam boards and also practice papers for AQA and OCR. I'm doing predicted papers for AQA, OCR, and EdXL this year. They're just not ready yet because I've been really ill. So if you also find anything missing on my website, do let me know. Just drop me an email because I've been really ill, I have been a little bit behind on putting things up. But my multiple choice questions, I would say, are mixed in difficulty. I'm also adding multiple choice questions now to the A-level masterclasses. So as well as you will get a whole set of the recorded lessons, which are all about exam technique and challenging questions. there are also practice questions and answers for each of the topics. And I'm now starting to add the multiple choice. And absolutely, you will be emailed as soon as the 2024 predicted papers are out. But if you are doing stuff now, then I suggest get on with the retrieval practice. And then maybe do the practice papers if you haven't already got those. And which exam board is most similar to WJEC? I would say Edexcel. Same for CIE, because Edexcel is more of an international exam board and it's got the least differences between them. All right. Thank you very much, guys. I'm totally losing my voice now, so I'm going to have a cup of tea. If you have any other questions, drop me an email and I will try and get back to you. Okay, guys. Bye-bye.